still see. What we're going to look at basically in a simple form you've already done. So binomial expansion is taking a binomial, so two terms, something like x plus y, raising it to some power, and multiplying it all out. So again, in a very simple version, it would be something like this. Now again, we're going to look at a little bit more complicated ones with higher exponents, different coefficients, but same concept. Basically looking at if this whole thing were multiplied out, what would it be? And instead of just foiling and foiling and foiling and foiling, we're going to look at a couple patterns and things that exist with this. So to start, we're going to look at something you may have seen before. This is called Pascal's triangle. So if you can see the pattern here, what's happening, yes, we're going to have ones on the end, but how we're getting those middle numbers, it's actually not just going to follow 4, 4, 4. Where these numbers are actually coming from is by taking the two numbers above it and adding them together. So 1 plus 1 gives me 2. 1 plus 2 gives me 3. So to get the numbers that fall below, so 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then again I've got my 1s here on the end. So we'll go ahead and add one more row. So this would be 1, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and then again I've got 1 on the end. So that is Pascal's triangle. It keeps going for forever and forever and forever as long as you want to keep adding those rows. Now how this relates to binomial expansion is actually kind of interesting. So we're going to take a really simple example of a binomial. All right, I'm going to take x plus y. And what I'm going to do is I'm going to raise x plus y to certain exponents. So let's say I take x plus y and I raise it to the 0 power. Well, anything to the 0 power is just 1. All right, let's take x plus y and raise it to the first power. Well, that's x plus y. All right, the example we just did, x plus y squared is x squared plus 2xy plus y squared. All right, x plus y to the third power. So if you were to actually do x plus y times x plus y, FOIL it out, and then multiply it by another x plus y, that resulting answer is going to be x cubed plus 3x squared y plus 3xy squared plus y cubed. All right, now I'm going to go ahead and show you what x plus y to the fourth is, and you may start to see this pattern if you haven't already, and how it relates to Pascal's triangle. So x plus y to the fourth power would be x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. All right, so you're hopefully starting to see some of these patterns. There's three things that we really want to look for here. One of them, look at what's happening to your x's. Okay, so the x is the first term of that binomial. So in each of these expansions, notice how your x keeps, the exponent on the x keeps getting smaller. So 1x to no x's. Squared to the first, none. Cubed, squared, 1, none. And that continues. X to the fourth, cubed, squared, 1, and none. All right, then let's look at our y. Okay, look at the y term and how those exponents keep getting bigger. 0y's, y to the first. 0y's, y to the first, y squared. 0y's, y to the first, squared, cubed. 0y's, y to the first, squared, cubed to the fourth. So the y one keeps getting bigger. All right, also notice how high those exponents get. All right, the exponent that the x starts with and the y ends with is whatever power you were raising it to. So that makes sense. I mean, if we're foiling it out, it's not going to be higher than that exponent. And the last thing that you probably notice and how this actually relates to Pascal's triangle is looking at the coefficients. So each term, remember, is what's being added. So those are our terms. Each term really has three components. You've got your x, you've got the y, and then you have the coefficient. Now, these are going to look a little bit different if there is a number in front of that x and that y, and we'll get there in a little bit. But for now, just notice how that coefficient matches the numbers on Pascal's triangle. So by following that pattern, we can figure out what this expansion is going to be. So without foiling out x plus y to the fifth, I know that it's going to start with x to the fifth. The next coefficient's 5. The x is going to get smaller. The y is going to get bigger. Next term, coefficient, x gets smaller, y gets bigger. Coefficient, x gets smaller, y gets bigger. Coefficient, x gets smaller, y gets bigger. And then x gets smaller and y gets bigger. And that's your expansion. It's a lot faster than actually multiplying this whole thing out. All right, so what we're going to look at now is how to find, let's say I needed to find a specific term of this binomial. Let's say that binomial, instead of just being x plus y to the fifth, is like 2x minus 7y to the 57th. And let's say I wanted to find a specific term in that binomial. Well, I'm not going to want to write out that many terms of Pascal's triangle. So there's another way to get those coefficients without using Pascal's triangle. And before we get there, I forgot I threw this extra example in. Let's go ahead and work one out using that Pascal's triangle. And let's look at one with coefficients. So we're going to follow the same idea. We're going to have the coefficient. Each term is going to have the coefficient. It's going to have 2a raised to some power, and it's going to have negative 3b raised to some power. All right, so what we're going to do is we're going to start, I'll go ahead and write that row of Pascal's triangle. So this row was 1, 4, 6, 4, 1. Okay, so that was that row of Pascal's triangle. Again, you'll notice the power is always going to be that second to last and second number. Okay, so again, we're going to start with coefficient, which is 1. 2a gets raised to an exponent, and that's going to start with the biggest exponent, which is 4. And then negative 3b is going to get raised to an exponent, which in this first term is just 0. So that's just going to go away. So this is just going to be 2a to the fourth, which is going to be 16a to the fourth. Then we go to our second term. I get my coefficient. 2a's exponent is going to go down. Negative 3b's exponent is going to go up. So this is going to become 4 times 2 cubed, so 4 times 8 times negative 3. So that's going to be a negative 24a cubed b. I don't know why I got negative 24. So sorry, that's a negative 3 times 8. That's negative 24. Negative 24 times 4, that's going to be a negative 96 a cubed b. All right, so now let's go to our next term. Let me switch up colors so we know which one goes with which. So I have coefficient. Next coefficient is 6. 2a gets an exponent. That exponent's going to be smaller. That one's now 2. Negative 3b gets an exponent. That one goes higher. That one's now 1. So now I have 6 times 4 times 9, which should be 216. And then I've got a squared, b squared. All right, then we'll go to our next term. So next coefficient. The next coefficient is back to 4. 2a's exponent goes down. Negative 3b's exponent goes up. So now I'm going to have 4 times 2 times a negative 27. So that's going to be a negative 216 a b cubed. Then we go to our last term. So the last coefficient is 1. 2a's exponent is down to 0. And then I'm going to have a negative 3b to the fourth. So negative 3b to the fourth, that's going to be 81a to the fourth. So this is your final expansion. Now again, as you get used to this, this will probably seem a lot faster. It's really kind of up to you if this is a method you want to use. If you want to just FOIL it out, that really is okay. But I want you guys to kind of see these relations. And again, like I talked about, we're about to look at some with some really big powers that you wouldn't want to multiply out just to find one specific term. And we're going to show another way to get those besides Pascal's triangle. Okay, so What we're going to do is we're going to use a formula that's probably going to look pretty familiar if you saw this in geometry, if you did permutations and combinations. So if you did permutations and combinations, then this is going to look familiar. It actually has another purpose, though, besides using it for permutations and combinations. What this can help us do is to evaluate the coefficients of a binomial in its expansion. So if you notice, this looks like a fraction. This is not actually a fraction. It's just n over r. N is the power of the binomial. R is the term minus 1. So what that means basically is if you're trying to find the fifth term, then that R value is going to be 4. The reason for that is because we're starting basically with our 0, is with a 0 placeholder. So if R is 0, that corresponds to the first term. So if R is 7, then that corresponds to the 8th term. Okay, so now let's look at kind of how this works. So to start, we're just going to evaluate this. We're not going to talk about where it is in terms of that placeholder. We're just going to actually use the formula to figure out what numerical value this has. So 5 over 4 written like this has an actual numerical value. So what we're going to do is we're going to use this factorial formula. So this factorial formula, it's 5 factorial over 4 factorial, and then 5 minus 4 factorial. So if you don't remember how factorials work, what you do is you take the number and you multiply by every whole number that follows. So 5 factorial is 5 times 4 times 3 times 2 times 1. 4 factorial would be 4 times 3 times 2 times 1. 1 factorial is just 1. And what's really nice about these is you'll notice a whole lot of things cancel out. So this whole thing is just the number 5. All right, looking at the next one. So this is going to be 8 factorial over 5 factorial, 3 factorial. So 8 times 7 times 6 times 5, 4, 3, 2, 1 is all going to cancel out with 5 factorial. So that just leaves me with 3 times 2 times 1. Well, 3 times 2 times 1 is going to cancel out with the 6. So this whole thing is just 56. All right, so again, this is just evaluating. Now we're going to talk about what this actually means. So what this corresponds to. The number at the top corresponds to basically the exponent of that binomial. And so it tells you at the top, n is the power of the binomial. So what that means is if we have an expansion, this would be an expansion of, let's just say it's x plus y to the 5th power. All right, so it would be something to the 5th power. Specifically, the term that this is the coefficient for is the 5th term. Because remember, that bottom number is the term minus 1, okay? Or r plus 1 is the term, if that's easier for you to see. So this stands for the 5th term in a 5th degree binomial expansion. All right, this next one, this would be something raised to the 8th power, okay? So this would be raised to the 8th degree. Or 8th power, I should say, not 8th degree. And then this would be the 6th term of that expansion. So that's the coefficient of that 6th term in that expansion. Okay, so now these bottom ones, what these are going to be are really kind of the easiest ones to figure out. These are ones that relate to Pascal's triangle, the kind of easy to see ones. Any power at the top, it does not matter what that number is, if it's over 0, it's going to end up as 1. If you want to work it out algebraically, you can definitely see that. But this ends up as 1 because if you think about 0, that corresponds to the first term. And for every expansion, the coefficient of that first term is 1. All right, n divided n over n. So if those numbers are the same, all right, doesn't matter what the degree is. Once they're the same, that's the last term. Because one thing you probably noticed, if it was a third degree expansion, there were 4 terms. If you were raising something to the 5th power, you had 6 terms. So there's always one more term in that degree. So this one also works out to be 1. Basically, this is the last term. And the last term always has a coefficient of 1. All right, looking at the next one, n over 1. This is always going to correspond to the 2nd term. So the coefficient of the 2nd term is always n. And it's always going to work out that way algebraically. And then n minus 1 at the bottom, that's the 2nd to last term, which is also going to always work out to be n. And those are just some shortcuts to kind of help you, and that's something you probably noticed when we were looking at that Pascal's triangle, where the first and last number were always 1, the second and second to last were always the same as the power of that binomial we're actually expanding. All right, so where this comes in is the big, ugly binomial theorem. Now, don't let this intimidate you. This is going to just follow the same pattern we just did using Pascal's triangle. This is just writing it in the very mathematical way. So don't let this stress you out. We're going to just put this into action and actually work one of these out. All right, so we're going to expand 2a plus b to the third power. Now, I know you could probably FOIL this out pretty quickly, but I want you guys to see how this corresponds and how this relates so that you can find specific terms of other binomials a little bit easier. So in order to expand this using the binomial theorem, all right, so instead of Pascal's triangle, I want you to see how this corresponds to the binomial theorem. We're going to do the same thing that we did earlier, okay? Every term is going to get a coefficient. It's going to get 2a raised to some power, and it's going to get b raised to some power. And we're going to do that for every single term. So the first part is the coefficient. So the first coefficient, we're going to go ahead and write those numbers using that formula we just talked about. So the number at the top is 3 because it's a third degree. The number below that, we're going to start with 0 because that's the first term. Then 2a gets an exponent. Now, how that exponent specifically relates to these numbers is actually also something that's really helpful. That exponent is going to basically be the top number minus the bottom number. So that's going to be 3. Then b gets an exponent. B's exponent is always going to be the bottom number. So we're just going to go ahead and write this whole thing out, and then we'll go through and simplify it. So my next term, I need a coefficient, so it's 3, 1. Top number stays 3 because that's the power we raised it to. Bottom number is just going to keep going up by 1. 2a gets an exponent. 2a's exponent is 3 minus 1. b gets an exponent. That exponent's 1. Next term, 3, 2 is the coefficient. 2a to the first power, 3 minus 2, and b to the second power. Then last term, 3, 3. We know we're done at this point because now these are the same number. 2a's exponent is now going to be 0. B's exponent is going to be 3. Remember, b's exponent will be that bottom number. The 2a exponent is basically the top minus the bottom. All right, so now we're going to go ahead and actually evaluate this. So 3 over 0, okay, this is what we just talked about. Anything that's over 0, that's going to end up being 1. So this is going to be 1 times 8a cubed times 1. Anything over 1 is the top number. So 3 times 4a squared times b. Anything, and then it's 1, basically 1 away from the end. So n minus 1, this is also going to just be 3. And then with the same, it's just 1. So this ends up being 8a cubed plus 12a squared b plus 6ab squared plus b cubed. Again, I know something like this is probably easier to multiply out, but I want you guys to see kind of how it corresponds to that theorem, because now when we look at a question like this next one, it'll be a little bit easier. All right, so we want to find the 7th term of this expansion. So if we're only looking for a single term, we don't really want to write out all 11 rows of Pascal's triangle. We also probably don't want to FOIL this whole thing out because it's going to take a really long time. So this is why it's helpful to use the shortcuts that we just talked about. So to find the 7th term of this expansion, remember, we're going to start with a coefficient. It's probably the most important thing for us to determine. Well, since the original expansion was raised to the 10th power, keep hitting the wrong buttons, then the top number here is going to be 10. Since I'm looking for the 7th term, the number at the bottom is going to be 6. Because remember, r plus 1 is the term. Okay, so 7th term is going to be 6 plus 1. So r here is 6. So that's my coefficient. That coefficient gives us all of the rest of the information that we need. So now what we do is we take the first part of the binomial, and we give it an exponent. So x squared's exponent is going to be 10 minus 6. So that's going to be x squared to the 4th. Then we also need the second part of that binomial to have an exponent. The second part's exponent is just the bottom number. And one thing you may have already noticed as well, you'll probably notice those two numbers always add up to your total expansion. Now again, that's not what the final answer is going to look like because this is obviously going to be 8, but at this step, those two numbers are going to add up to that. All right, now let's go ahead and finish this off. So I need to evaluate that 10/6 using that n factorial formula. So it's 10 factorial over 6 factorial, 4 factorial. So 10 times 9 times 8 times 7, 6, 5, 4, 3, 2, 1 is going to cancel out with the 6 factorial. That's going to leave me with 4, 3, 2, 1. All right, so 4 and 2 cancel out with the 8. 9 and 3 can reduce to just a 3. So I've got 21 times 10, which is just going to be 210. So this is 210 times x to the 8th times, and remember, all of this is multiplied together. There are no pluses or minuses in between here. This is one single term. So then it's times 2 to the 6th, which is 64, y to the 6th. Go ahead and multiply 210 times 64. You end up with 13,440 x to the 8th, y to the 6th. And that is the 7th term of that expansion. All right, let's go ahead and look at this last one. So same idea, we want the 5th term of this expansion. So we start with the coefficient. 7 is on top. 5th term means we want 4 at the bottom. 3ab gets an exponent. 3ab's exponent is 7 minus 4. Negative c gets an exponent. It's the bottom number. Let's evaluate 7, 4 using that factorial formula. So 7 factorial over 4 factorial, 3 factorial. So 7 times 6 times 5. 4, 3, 2, 1 is all going to cancel out. Well, 3 and 2 are going to cancel out. So that leaves me with 35 times 27 a cubed b cubed. And then negative c to the 4th is now going to become positive c to the 4th. Multiply 35 by 27. End up with 945 a cubed b cubed c to the 4th. All right, so that is it for binomial expansion. Again, just really trying to kind of relate some of the Pascal's triangle stuff and showing you guys how you can take that really a step farther. Same kind of format for today. You've got your practice problems and your check. If you need help, you can jump in that Zoom session, or just feel free to send me an email or fill out a video request.